Okay, so I'm going to sit down and do the Chapter 3 review. Realistically, the best thing you could have possibly done is done the whole review and treated it like it was a test before watching this video. So if you haven't started the review yet, you shouldn't. You should maybe pause the video, stop the video, do the review, and test yourself, because watching me do the problems is completely different than doing problems by yourself. So that if you do the problems by yourself correctly, that's a better indication that you're ready for the test than if you watch me and think you understand how I do the problems, because watching and doing are completely different. Absolutely guaranteed that the test will be likely shorter than this review. This review has 40 problems. Some of the problems have multiple parts. I would suspect that the test will have 25 to 30 questions worth kind of 3 or 4 points apiece to give you your 100 points. There's a decent number of problems that aren't going to require any algebra, so those are hard problems for me to give partial credit. So on those problems, you just have to make sure to just nail them. And can't share calculators on the test. So if you don't have a graphing calculator, then you're going to have to wait till somebody finishes their test to be lent a calculator. But you can't exchange calculators during a test. It's too easy to exchange answers. Okay, so the first 4 problems on the Chapter 3 review give me a short paragraph, and the instructions say determine whether y, the equation defines y as a function of x. It says hint, solve the equation for y kind of when necessary, then use your calculator. So I'm going to graph each of these functions. If the graph fails the vertical line test, I'm going to say no. If the graph passes the vertical line test, I'm going to say yes. And I'll get into that real quickly here. So I'm going to graph this first function, which is x minus 3 squared plus 4. When I sketch a graph, it's just going to be a parabola. Looks something like this. Because there are no vertical lines that can be drawn to touch the graph in more than one place, I say that this passes the vertical line test as opposed to fails the vertical line test. Because it passes the vertical line test, that is, I can't draw a vertical line to touch the graph in more than one place, an appropriate answer would be yes for this. Or we can say y is a function of x. That's what the yes means here. So either one of those would be appropriate. It would be nice if on your test paper you showed the graph that you came up with and showed that it passed the vertical line test. But if you didn't show me your calculator work, that's okay. Question 2 is where this hint up here makes a difference. It says hint, solve the equation for y, because if I'm going to graph on my calculator, an equation needs to be solved for y. So I'm going to follow my hint and solve this for y by first subtracting 4 from both sides and then square rooting. And when I introduce a square root into a problem that doesn't have a square root, I need to plus or minus. So I'm going to get plus or minus the square root of x minus 4 equals y, because on the right side, square rooting cancels out the square. It would be wrong to change that 4 to a 2. When I graph this on my calculator, I can't do the plus or minus as one function. I have to do 2 functions. The 2 functions I'm going to enter on my calculator is y1 is the square root of x minus 4 for the plus part of the plus or minus, and then y equals negative square root of x minus 4 for the minus part of the plus or minus. And so I'll do that. Hopefully my calculator's displaying well. So I'm going to go second square root of x minus 4 and then negative second square root of x minus 4. My calculator's going to draw a half parabola on its side, I believe. So this graph looks more or less like this. My graph doesn't have to be that accurate to be able to answer the question. This function, this picture, we say it fails the vertical line test. Because it's possible to draw a vertical line to touch the graph in more than one place. When my picture or graph fails the vertical line test, I can either write no for an answer, or I can say y is not a function of x. The no implies that. So either of those would be acceptable answers to problem 2 on the review. Three, I could graph without my calculator, but I'll use my calculator to sketch a graph. 3 is in the same bank of problems. I want to see if y is defined as a function of x or not. This is another equation that's not solved for y, so I'm following the hint that I wrote to say that says solve the problem for y first. For this one, I'm just going to subtract x minus 3 squared from both sides first, and then square root plus or minus square root. On the right side, the square rooting will cancel out the square because there's just one item that's being squared. On the right side, you can't make the 9 a 3 and make this an x minus 3. You can't take the square root of each piece. The minus sign keeps that from being legal. The entire quantity under the square root would have to be squared before you can cancel out the square root symbol. The minus between the 9 and the x squared make the x minus 3 squared make it so it would be illegal to cancel out the square root or to reduce this problem at all. Because of the plus or minus, when I go to hit my calculator, I'm going to graph two functions, a y1 and a y2. The y1 is going to have the positive, so I won't put a sign in front of the square root. The y2 is going to have the negative. So same sort of deal. I do second square root and then 9 minus the quantity x minus 3 squared, close out my parentheses, and then negative 9, negative parentheses, negative square root of 9 minus the quantity x minus 3 squared, close out my parentheses. This is really supposed to be a circle, but it's probably going to look more like an ellipse than it is a circle. And I did something horribly wrong on the top half, because the bottom half gives me the half circle. The top half should have also given me a circle. I entered something wrong here. And the wrongness I did is, if you look at the bottom version of after the 3 there's a parentheses and a square, I missed this parentheses. So this should be parentheses squared, parentheses. That'll fix things up perfectly and give me the circle that I'm looking for, something that maybe doesn't look perfectly like a circle on my calculator, but is supposed to be a circle. So that's the graph my calculator gave me. It makes it look like a football, but for our purposes it's okay. In terms of answering this question, I don't need that accurate of a graph. This graph also fails the vertical line test because I can draw a vertical line to touch the graph in more than one place. So the answer is going to be no. So I'm going to say either no you can write for an answer, or you can say y is not defined as a function of x, or y is not a function of x. Either answer for my test would be completely fine. I'm not that picky where I need to see the verbiage. 4 is a friendly question in terms of I don't need to do any algebra to be able to graph it because it's already solved for y. So when I do 4, I cleared out the functions that I previously graphed. Now I'm going to graph x minus 1, and that's a half parabola on its side, but it doesn't have the bottom part because I don't have the plus or minus. This graph looks something like this, and this, because it's impossible to draw a vertical line to touch the graph in more than one place, we say it passes the vertical line test. So the answer is going to be yes to this. or I can say y is a function of x. Either answer would be acceptable. So that's the first 4 problems. They all have the same instructions, so I did them all the same way. 5 through 8 want me to find the domain and range and write interval notation where appropriate, and they give me a graph. If the graph is a series of disconnected points, then the domain and range is going to be written in set notation. The domain is going to contain the x coordinates of the points that are labeled. The range is going to contain the y coordinates of the points that are labeled. So when I go to do problem 5, because it's just a scattered set of 4 points, the domain and the range I'm going to use squiggly set brackets for. And for the domain, I'm going to find the x coordinate of each point, which would be 5, 3, 7, and 4, and I'm going to write 3, 4, 5, 7 just to write them in order, but you just need the x coordinate of each of the 4 points. When the points are disconnected, you write a domain using set notation, and you just take the x coordinates of the points. For the range, I need the y coordinates of the points. The y coordinates are -1, 2, 2, and 6. When I write the range, I could write those 2's twice, but it's not necessary, and usually as mathematicians we try to be efficient. So I'm going to write the numbers -1, 2, and 6. If you had 2 2's, it's not wrong, but it's writing more than you have to. And if you wrote the numbers in a different order, that's also okay. I took the time to write the numbers from smallest to largest, but if you wrote 2, 6, -1, that would be okay. If you showed interval notation, like this would be a wrong answer for number 5. It would be wrong to say the domain goes from 3 to 7. It would be equivalently wrong to say the range goes from -1 to 6. That would only be appropriate if the points were connected. Since they're not connected, the values in between 3 and 7 for the x's and in between -1 and 6 for the y's aren't part of the graph and shouldn't be part of the domain. For number 6, the points are connected, so I expect my domain to have interval notation, and I'm only going to show 2 numbers in my domain answer. Similarly, I'm only going to show 2 numbers and use interval notation to show my range. This is the friendliest kind of graph because the edges are labeled, and I don't need to extend the graph. To do the domain for this graph, I need to find the point that's furthest left and its x value, and the point that's furthest right and its x value. The furthest point that's furthest left on this graph is the point 0, -5. Its x coordinate is 0. I'm going to put a square bracket because that point's on the graph. I'm going to go 0, and then I'm going to end my domain by writing 5, which is the x coordinate of the far right point, in another square bracket. So I get square brackets on domain and ranges that essentially don't get infinities. For the range, I need to pick off the bottom point and its y. The point 0, -5 is the bottom point, its y is -5. I also need the top point and its y. The point 3, 4 is the top point, and its y is 4. When I write the range, I go from bottom to top, take the y coordinate of the bottom point, and then the y coordinate of the top point. So the best answer for number 6, the domain would be 0 to 5, the range would be -5 to +4. All square brackets because I didn't have to extend the graphs off to any infinities. The next 2 pictures, 7 and 8, both the graphs need to be extended. 7 only needs to be extended in one direction. The right edge at 0, 2 doesn't need to be extended because the right edge is dotted. But the left edge, as this graph goes, it goes down and to the left forever. It's going to be extended all the way to the far left edge of the x-axis and all the way to the bottom of the y-axis. So because there wasn't a period at the end of this graph, it needs to be extended in the direction that it's going, which is all the way to the left and all the way down. Now that I've extended the graph, I only have 2 points, so they're the only points I can possibly use to answer my domain and my range. For the domain, I need the far left point and the far right point and their x coordinates. The far left point is this double negative infinity. Its x coordinate is negative infinity. Negative infinity is going to be the first thing I show in the domain. I always get round brackets around infinity or even negative infinity because the graph doesn't actually get there. It just goes on forever. If you put a square bracket, it would mean the graph would stop. It would get to infinity and stop, but infinity doesn't exist. The graph just never ends. And for the end of my domain, for this problem, I'm going to write 0 with a square bracket because that is a point on the graph. That's the x coordinate of the far right point. To do the range, I need the bottom and its y. And the top point and its y. Similarly, the range is going to start off with a negative infinity, round brackets and all infinities, and it's going to end at 2, which is the y coordinate of the top point. And that's all there is to do for that. 8 doesn't have any points labeled. I could have labeled the x-intercept, but that would have been cruel. The graph needs to be extended up and to the right, and up and to the right it extends to a double positive infinity, and it needs to be extended down and to the left, and down and to the left it extends to a double negative infinity. Now I have 2 points. I always have to have at least 2 points labeled to do the domain and the range, because I need 1 point for each generally. For this one, the domain is going to pick off the x coordinates of the far left point and the far right point. So my domain is going to be negative to positive infinity. And my range is going to pick off the y coordinates of the bottom and the top point, and the domain and the range are both negative to positive infinity in this case. Alright, hopefully that was good. I know all these problems are you do in intermediate algebra, so hopefully this part is feeling like review. Next 3 problems give me equations. They ask me to find the domain using algebra. It says to write my answer in interval notation. I wouldn't be so picky on the test that if you gave me something different than interval notation that was correct, I probably wouldn't take points off. To find the domain of 9, I'm going to ignore the numerator. If I set the numerator equal to 0, I actually get an x-intercept. 4 is an x-intercept of this graph. It has nothing to do with the domain. To find the domain, because it's a fraction, I solve the denominator of this equal to 0, and that gives me the numbers to exclude from the domain. It doesn't give me the domain, but it gives me the important numbers. So I'm taking the denominator, which is x squared plus 6x minus 7, setting it equal to 0 to get the numbers to exclude from the domain. Because there's a square, I need to solve by factoring. This factors into x plus 7 times x minus 1. Once I have something both factored and set equal to 0, I split each factor up, set them separately equal to 0. So the numbers I need to exclude from my domain are -7 and +1. It would be okay if on a test you said the domain in words is all real numbers except -7 and -1, -7 and 1. This would be an acceptable answer. And without that extra comma. It isn't what I asked for because I asked for interval notation, but this would be an acceptable answer. To get interval notation, generally we start off with an interval that starts at -infinity. It goes to the first number that I'm excluding, which is -7. Round brackets excluded. The next interval to exclude the -7 needs to pick up with the -7 and go to the next number I'm excluding, which is 1. Then a union symbol. The last interval is going to go from the 1 that I'm excluding to positive infinity. This would be the interval notation for the domain that's technically asked for. So either writing the domain in words, saying the domain is all real numbers except -7 and 1, or writing the interval notation, the all round brackets. If you put a square bracket on any of the -7s or the 1s, it's not excluding it from the domain. Ten is finding the domain of a square root. The algebra to find the domain of a square root is to take what's under the radical and set it greater than or equal to 0. And unlike the algebra for finding the domain of a fraction, doing the domain computations for the square root actually gives you the entire answer, not just numbers to exclude. So I took the radicand, which is the x plus 5, set it greater than or equal to 0, subtracted 5 from both sides. This is technically a correct answer. It wouldn't be wrong if I said the domain is any number x greater than or equal to -5. It's not what's asked for because what's asked for is interval notation, but that is actually correct. The domain computation for a square root gives you the domain written correctly, just not in interval notation. Saying x is greater than or equal to -5 is the same thing as saying -5 to infinity, and square bracket on the -5 because I'm including the -5 in the answer. 11 asks me to find the domain of a polynomial, which would graph to be a line. There's no algebra to find the domain of any polynomial. The domain is going to be all real numbers. If you do any algebra, the algebra for this one, you'd probably get 6, or 3, should I say. You set 2x minus 6 equal to 0. What you'd get is 3, which happens to be the x-intercept. But the x-intercept has nothing to do with the domain. It's not a far left or a far right endpoint. This is actually a picture of this graph. And this graph has a domain from negative to positive infinity because it goes on forever to the left and forever to the right. The domain, if I had a graph, would be the x-coordinate of the far left point, the x-coordinate of the far right point, and that would be negative to positive infinity. The 3 that you'd get using algebra would give me the x-intercept, but the x-intercept isn't a far left point or it isn't a far right point, so it has nothing to do with the domain. The x-intercept 3 is just a random point on the graph, which maybe is an interesting point, but it has nothing to do with the domain because that point isn't at the extreme left or the extreme right. So for us, we had 3 kinds of domains. We have domains of fractions. For those, you have to set the denominator equal to 0. You ignore the numerator. We have square roots. Where you take a radicand and set something greater than or equal to 0. We'll say radicand, but the radicand is what's under the radical. And we have polynomials, of which problem 11 is, and there's no algebra. So I did one of each in my review. I doubt that there'll be one of each on the test, but there could be. So depending on how the function is written, you need to be able to know the appropriate algebra, and then after you do the algebra, how to take the answers from the algebra and write an answer. 12 through 15 want me to add, subtract, multiply, compose functions 12 wants me to find f minus g of x. To find f minus g of x, I'm going to write two parentheses separated by a minus sign. In the first parentheses, I'm going to put the right side of the f function, which is x squared plus 3x minus 4. In the second parentheses, I'm going to put the right side of the g function, which is 7x minus 7. And I'm just going to combine. I'm going to do the algebra to simplify this and combine like terms. The first parentheses that I put in, it really wasn't necessary. I'll just drop it without doing any sign changing. The second parentheses was needed. The minus in front of the parentheses is going to attach to the 7x. It's going to change the sign on the 7. So I'm going to make this a minus 7x and a plus 7. Now I'm going to combine like terms. I'm going to make a 3x and a minus 7x into a single term, and a minus 4 and a plus 7 into a single term. When I do that, the x squared is not going to change. The 3x minus 7x turns to a minus 4x, and the minus 4 and the plus 7 turns into a 3. If you start with a problem that has some squares and you didn't multiply it out, we usually want you to factor that answer, and that's actually factorable. Hopefully your factoring skills are sharp enough that you know that that factors into x minus 1 times x minus 3. If your factoring skills aren't where they should be, you can come visit me. I'll try to teach you individually how to factor. I also have videos in my intermediate algebra lectures that show how to factor. So the best answer for problem 12 is f minus g of x equals x minus 1 times x minus 3. 13 is a messy problem. It wants me to find f composed with g of x. To find f composed with g of x, the first thing I do is I write the f without the x. Then I leave a parentheses where the x's were. So let me do that now to get started. So f composed of g of x, I write the f function, which is x squared plus 3x minus 4. I write it without the f. I leave a parentheses where the x's were. And then I write the right side of the g inside the parentheses. So I'm going to write a 7x minus 7 in both parentheses, and then it's just simplifying. The first simplifying is doing 7x minus 7 quantity squared, and that's actually a foiling problem. That's 7x minus 7 times 7x minus 7. So I'm going to do the firsts, which are 7x times 7x, and get 49x squared. And then the outers, which are 7x times minus 7, which is minus 49x. Then the inners, which are minus 7 times 7x, which is minus 49x. And then the lasts are minus 7 times minus 7, which is plus 49. So that's doing this part of the simplifying. Now I'm going to do this multiplying. I'm going to go 3 times 7x and 3 times minus 7. 3 times 7x is going to be a plus 21x. 3 times minus 7 is going to be a minus 21. And then I bring down this minus 4. I need to combine like terms. Didn't leave myself room to do that. The 49x squared I'm going to bring down. That's not like anything else. But these terms, the minus 49x minus 49x plus 21x, can be combined. I'm going to use my calculator to combine those numbers because I'm afraid I'll mess up. So I go minus 49 plus 21, and I get, that's not right, minus 49, that's what I'm doing, minus 49 plus 21, I get minus 77x. And then I have a positive 49 minus 21 minus 4. So 49 minus 21 minus 4, which is 24. It's actually a plus 24. would be ultra impressed if you could factor this. I believe that this does factor. But I don't expect you to factor something with this kind of numbers, but let me see if I can actually do this. So I'm doing something slick here because I teach. I should be able to do something slick. Really? Does that actually work? I think that actually works. Well, my quick effort to factor this doing something slick. Let me try one more time. Plus, yeah, it should be u plus 4 times u minus 1. So 7x minus 7 plus 4 times 7x minus 7 minus 1. 7x minus 3 times 7x minus 8. Oh, I think that actually works. 20. Yes, this actually factors. And in order to factor this sanely, I had to do some sort of U substitution trick that you probably hadn't seen before. If you followed this, it's quite impressive. I would not expect you to try to factor that. This would be an okay answer. This would also be a wonderful answer. So I'm going to write an answer in a nice form. I'm going to write the problem and then the answer. If you want to know what I did there to get this factored slickly, come visit me and I'll show you. It's a nice trick for factoring something that was horrible that is relevant to this problem. But in general, if you try to do bottoms-up factoring on this, I would suspect that the numbers would get so big that it would be too hard to factor. So when numbers are that big, I'd not expect you to factor. If you're taking the test and you want to ask me, hey, do I really need to factor this? Come up and ask me and I'll tell you, no, the numbers are insanely big, don't worry about it. Or if the numbers are mildly big, I might say, yeah, give it a try. So I did something sneaky here to get this factored. If you're interested, come visit me and I'll show you what that sneak is, just so you can maybe have that skill when you go to calculus. Problem 14 wants me to find f plus g of 5. The first thing I'm going to do is pretend the problem said x. If the problem didn't have a 5 and it had an x, to do f plus g of x, I'd write the right side of f of x, which is x squared plus 3x minus 4, and the right side of g of x in parentheses separated by a plus sign. The nice thing about this problem is I don't have to simplify with an x because I'm allowed to change the x to a 5 before I simplify. So I found out what the problem would look like if it had an x instead of a 5. Didn't simplify that. Now I shove the 5 in for x. I'm going to simplify with the 5 because it's easier to simplify with the 5 than it is the x. So I'm going to work on the first parentheses. 5 squared is 25. 3 times 5 is 15. In the second parenthesis, 7 times 5 is 35. Now I have it so I can make each parenthesis down to a single number. The first parenthesis, 25 plus 15 is 40. 40 minus 4 is 36. The second parenthesis, 35 minus 7 is 28. And if I add that, I get 64. So my answer for f plus g of 5 is just going to be 64. If you just wrote the number 64 and didn't include the problem with your answer, that's okay. 15 wants me to do g composed with f of 4. First, I'm going to do g composed with f of x. To do g composed with f of x, I write the g function, 7x minus 7, without the x. I leave a parenthesis where the x was. Inside the parentheses, I put the right-hand side of the f function, which is x squared plus 3x minus 4. I don't need to simplify that because in this problem I'm allowed to change the x to 4 before I simplify. So I'll do that. I'm going to go 7 times 4 squared plus 3 times 4 minus 4 minus 7. Notice here I didn't put the 4 in a parentheses when I squared it. If the 4 was negative, I would have needed that parentheses, but because the 4 is positive, the parentheses weren't really that big of a deal. So I'm simplifying the inside of the parentheses. I did 4 squared, I did 3 times 4. This parentheses, 16 plus 12 is 28, minus 4 is 24. So I get 7 times 24 minus 7. It's 140. Is that 168 minus 7? I believe that's 161. But I'm going to do that on my calculator off to the side to make sure I did it right. Yeah, I did it right. So for my answer, I'm going to say G composed with f of 4 equals 161. If you just wrote the number 161 and didn't write the problem with the answer, that's okay as well. 16 wants me to find the difference quotient. The reason I put a couple of these on the test is because I know you see those in calculus a lot early off. So you might as well get used to them now. What I need to do is replace the f's in the numerator. I know how to replace the f of x, but I don't know how to replace the f of x plus h. So for my f of x plus h in the numerator, I'm going to find out what it equals to by taking the x in the original function and replacing it with x plus h, and then simplifying by distributing the 2 through the parentheses. Now I know what to change each piece in the numerator of the difference quotient to. In the numerator, I'm going to change the first f that I see to 2x plus 2h minus 3. I'm going to change the second f that I see to 2x minus 3. I'm going to leave the denominator h because it didn't have an x. Now I'm going to simplify. The first parentheses I put in the numerator wasn't necessary. I can drop it without changing. The second parentheses I put in the numerator was necessary. I need to change the sign on the 2x and on the 3. Now in the numerator, the 2x's are going to cancel. The 3's are going to cancel. I'm going to be left with only a 2h in the numerator as well as an h in the denominator. Those h's are going to cancel. Fraction's going to go away. My whole answer is just going to be 2. For most different quotient problems, if you do them correctly, in the numerator, everything that doesn't have an x will cancel, and you'll be able to cancel out so it's not a fraction anymore. 17 wants me to do the same thing, so I need to know how to replace the f's in the numerator. The f in the numerator that I don't know how to replace is as f of x plus h, so I'm going to figure out what to put in for that. To figure out what to put in for that, I go to the function that's defined here and change the x's to x plus h. The x plus h quantity squared is a foiling problem that may not look like a foiling problem, but it is, so I'm going to FOIL it. I'll do the firsts, x times x or x squared. The outers, x times h is xh. I'm going to put a 1 in front of those to make it easier. The inners, h times x is also xh. I'm going to put a 1 in front of those. And my last h times h is h squared. So this bit is foiling x plus h times x plus h. Now I'm going to go 5x times 5 times x and get 5x. 5 times h and get 5h, and bring down the plus 2. These xh's can be combined together. So that's what f of x plus h is. Now I'm ready to answer the problem. The problem wants me to find f of x plus h minus f of x over h. I'm going to do that. I'm going to make a big parentheses, and inside it put the f of x plus h, which is x squared plus 2xh plus h squared plus 5x plus 5h plus 2. close the parentheses, put my minus sign. To the right of the minus sign, write what f of x is, which is x squared plus 5x plus 2. Leave the denominator, since it doesn't have an h, I'll leave it an h. Now I'm going to simplify. The first parentheses I put in the numerator, I'm just going to drop because it doesn't have a minus sign in front of it, a multiplication associated with it, or an exponent. I can drop that without any changing. This parentheses, I need to change each of these signs to minus. The minus in front of the parentheses causes all the signs to change, makes it a minus x squared, a minus 5x, and a minus 2. Now I'm going to cancel. The x squareds cancel, the 5x's cancel, the 2 and the minus 2 cancel. And the numerator, what I have left after I do the canceling is 2xh plus h squared plus 5h over h. I'm going to now factor out an h from the numerator and get equals to h times 2x plus h plus 5 over h. That was the denominator. I'm going to cancel out the h's. Denominator's gone. Factoring's gone from the numerator. The answer to this problem is going to be 2x plus h plus 5. For those of you that took calculus maybe recently, maybe in a high school class, this has something to do with the derivative of a function. So that was a monstery, messy problem. I'd like to think I wouldn't put something quite that messy on a test. The next problems don't have any algebra to do. I just have to understand the part of the graph that's being asked for. So I'll try to make it a little bit bigger. So this set of problems refer to this graph. The first thing it says is to find the x-intercepts. The x-intercepts are the points where the graph is on the touches or crosses the x-axis. For this particular problem, the x-intercepts are the point negative 4, 0, which is that point on the x-axis, and 0, 0, which is this point on the x-axis. Because here's the x-axis. If I look across the x-axis, those are the points on the x-axis, which make them x-intercepts. Number 19 wants me to find the y-intercept, so I look at the y-axis and see if my graph crosses any points on the y-axis, and it does. The graph crosses on the y-axis. The point 0, 0 is on the y-axis, which makes it a y-intercept. 0, 0 is a tricky point because it's both on the x-axis, so it's an x-intercept. It's also on the y-axis, so it's a y-intercept. Those are easy-ish problems. The harder problems are 20 and 21. And I very specifically included the same number in each of the problems just because that makes them harder. Problem 20, the negative 4 is to the right of the equal sign, so it stands for a y value. 20 wants me to find the x coordinate of any point that has a y coordinate of negative 4. That's this bottom point here. The answer to 20 is going to be x equal to negative 2. So because the number that was given is to the right of the equal sign, it's standard for a y, I'm asked to find an x. Whereas in 21, the number negative 4 is in the parentheses. It stands for an x and it wants me to find a y. So for 21, I want to find the y coordinate of any point that has an x equal to negative 4. So they both have negative 4s. If the negative 4 was written to the right of the equal sign, it stands for a y. I'm looking for an x. If the number negative 4 is inside a parenthesis, that stands for an x. I'm looking for a y. For an answer for 21, you could just, this is the point negative 4, 0. You can just say y equal to 0, or you can say h of negative 4 equal to 0. They both would be correct answers. So no algebra to do for any of these 5 problems, which makes it hard to give partial credit. To do the domain and the range, I need to extend the graph. The left side doesn't need to be extended because it has a period, but the right side needs to be extended, and it extends up and to the right to the double infinity. To do the domain of this, I need the x coordinate of the far left point, which is going to be negative 4. and the x-coordinate of the far right point, which is going to be infinity. So the domain for this is going to be the x-coordinate of the far left point, -4, comma, the x-coordinate of the far right point, infinity, square bracket on the -4 because it's a point on the graph, round bracket on the infinity because the graph never actually gets there. For the range, I need the y-coordinate of the bottom point, which is coincidentally a -4, and the y-coordinate of the top point, which is coincidentally an infinity. The range, I take the y-coordinate of the bottom point, -4, and then comma, y-coordinate of the top point, infinity. This is a rare problem where the domain and the range are the same. That doesn't normally happen, but it did in this case. It doesn't mean it can't happen, it just doesn't normally happen. More problems with no algebra. For 24, it gives me a picture and it wants to know the x-coordinates of where the graph is above and below the x-axis. So I'm going to reproduce this graph on another sheet of paper. Put only the numbers that I need. So in 24, the graph goes through the point 3, 0. I'm going to take the x-coordinate of that and write it down. And I'm going to extend the graph up and to the right to the double infinity, down and to the left to the negative infinity, negative infinity. The graph, the thing says, the problem says, what values of x is f of x greater than or equal to 0? And for what values of x are f of x less than or equal to 0? This graph I'm going to partition when I'm answering these questions. I'm going to cut the graph using the x-axis, and I'm going to look for the region of the graph that's below the x-axis. Below the x-axis is where the f of x is less than or equal to 0. And the part of the graph that's above the x-axis is where the values of f of x or the y's are positive or greater than or equal to 0. So this graph, the interval that's below the x-axis is from x equal -infinity to x equal to 3. Putting a square bracket on the 3 because of the or equal to with the infinity, with the 3. So the region between -infinity for x and 3 for x, the graph is below the x-axis, so that's the region where the f of x's or the y's are less than or equal to 0. And this next region from 3 to infinity, that's the region where the graph is above the x-axis or where f of x is greater than or equal to 0. I do square brackets because on the 3 because of the or equal to part with the inequality. So that's what's asked for in 24. Another problem where there's no algebra, and when there's no algebra, it's hard to give partial credit. I'll blow up the picture for 25. So 25 looks something like this. Didn't even show that because you don't need that. So I tried to be kind when I drew the problem, and I didn't show the vertex because you don't need the vertex to answer this question. The question is, for what intervals is the graph above the x-axis? And for what intervals is the graph below the x-axis? I need to extend the graph up and to the right to the double infinity, and up and to the left to the negative positive infinity. So the graph is above the x-axis here and here. Those regions where it's above the x-axis are disjoint. My answer to part A, to where the graph is above the x-axis, is going to be written with 2 intervals. The first interval represents this region, which is between -infinity and -5. The second interval I'm going to write with a union sign between is between 1 and infinity. So there's 2 disjointed pieces where the graph is above the x-axis. And then this region here is where the graph is below the x-axis, and it's a connected region, and it's between -5 and 1. So I blew the picture up. I extended the graphs because it needed to be extended. I only showed x coordinates, and then I tried to look at the x-axis, find out where the graph is above the x-axis and below the x-axis. Where the graph was above the x-axis, I created intervals, put those in for my answer to question A, where our f of x is greater than or equal to 0. And where the graph was below the x-axis, I created an interval and put that into B. '26 has a bunch going on. The C, D, E, and F are the easy parts, and the A and the B are the hard parts. I'm going to do the C, D, E, and F first, and then I'll go on another sheet of paper and do the A and the B. For the maximums and minimums, I think those are intuitive. For this particular graph in problem 26, the point -3, -8, although it's not the highest point on the graph, it's kind of a little bump. It's a little top of a hill. We call that point a local maximum. And this point, -1, -12, it's not the very lowest point on the graph, but it's a little valley. We call that a local minimum. So when I go to answer C, D, E, and F, C wants the values of x value of any local maximum. I'm going to say it's x equal -3. D wants the local maximum value, which is the y value of the maximum. I'm going to write y equal to -8. E wants the x coordinate of any local minimum, which is x equal to -1. And F wants the y value of that minimum, which is y equal to -12. So I'm looking for peaks and valleys to do local maximums and local minimums. That's the easy part. I think I might be able to squeeze the increasing right on this picture, right on this page. So the graph is increasing for when I move from left to right, it's going up. So for this particular graph, which needs to be extended down and to the left and up and to the right, there are two portions of the graph where it's increasing. This region right here, as I move from left to right, it's going up. And this region right here, as I move from left to right, it's going up. So the local maximum and the local minimums, the graph changes directions at those. To the left of the local maximum and to the right of the local minimum, this graph is increasing as I move from left to right, because on this part of the graph, to draw the graph, it has a positive slope, or it goes up as I move from left to right. Similarly for that part of the graph. So I would say this graph is increasing between x equal -infinity and x equal -3. And then again, it's increasing between x equal -1 and x equal infinity. Usually for increasing and decreasing, we put all round parentheses, because at the maximum or at the minimum, it's changing directions and it's not increasing nor decreasing. For the decreasing part of this graph is decreasing right there. It's to draw the portion of the graph between the local maximum and the local minimum. That's where it's decreasing, and the x values in that interval are -3 to -1. So I would say this graph is decreasing from -3 to -1. This is also hugely important in calculus. In calculus, you'll be asked to do these questions again, except you'll have to do calculus to answer the questions. You'll be given functions, and you'll need to do algebra or calculus to get the answer. 27 asks the same questions. Again, the C, D, E, and F are the easier ones. This point 3,4, it's at the top of the graph. It's a high point, so that's called a local maximum. This graph doesn't really have a local minimum. It doesn't have like a little valley, so I'm going to say there's no local minimum. And let me extend this graph. Pretend you didn't see that. I'm going to extend this graph like that. And when you print out your printout, it'll be extended for you, just because it makes it so there's no gray zone on the minimum. So this is what the graph is going to look like when you print it out. There's a high point but not a low point. So the values of x where there's a local maximum is the x coordinate of that point. The local maximum value is the y coordinate of the maximum. And because there isn't a low spot, I'm going to say there's no local minimum, so there's no local minimum value as well. If I want to extend this graph, this part of the graph that I'm going to make extend now, it's going to extend to negative infinity, negative infinity. This region of the graph, as I move from left to right, it's going uphill. So I'd say that region of the graph is increasing. So for this particular graph, it's increasing between negative infinity and positive 3. And then to draw the rest of the graph, as I go from left to right and I extend the graph down to the double or positive negative infinity, this piece of the graph is the decreasing portion, because as I go from left to right, it's going down. I'd say this graph is decreasing from 3 to positive infinity. So I extended the graph in both directions, wrote just the x coordinate, made intervals. The first interval from the bottom of the graph to the local maximum, it's going up. The second interval from the top of the graph to the bottom of the graph, it's going down. Going up is increasing, going down is decreasing. 28 wants me to find the average rate of change, as does 29. The average rate of change we could do pictorially, but we don't have to. The average rate of change is the slope of the line that connects 2 points. And the values that are given in this problem are the x coordinates of the points. To find an average rate of change, which you also do in calculus, for both problems 28 and 29, I need to get the y coordinates of the points that correspond to the value of x. So the first thing I'm going to do is find the y coordinate that connects with 4 by going 3 times 4 minus 2 squared minus 4, plugging 4 in for that x. This is going to give me 12 minus 2 squared minus 4, which is going to be 10 squared minus 4, which is going to be 100 minus 4, which is 96. We're also going to find the y coordinate that corresponds to f equals 5, which is going to be 3 times 5 minus 2 squared minus 4, which is going to be 15 minus 2 squared minus 4, which is going to be 13 squared minus 4, which is 169 minus 4, which is 165. So the average rate of change from 4 to 5 is the slope of the line that connects the point 496 to the point 165. Now I'm just doing y2 minus y1 over x2 minus x1. I get this just 69. So the answer to the average rate of change is the slope of that is the 69 over 1, which is just going to be 69, because I don't need to write it. Average rate of change is 69, or 69 over 1. So for each of problems 28 and 29, I just want to make points. In 29, the points I need are 0 comma something and 2 comma something. Those values are supposed to be x's. The average rate of change is the slope of the line that connects 2 points on a graph. The first y value I'm going to get, I'm going to plug 0 into the function, and I'm going to get 0. The second x value of 2 gives me the y value of, let me see, 2 cubed plus 6 times 2 squared. 2 cubed is 8. 2 squared is 4. The second y value is going to be 32. So the average rate of change, this is going to be easy algebra, which is the slope of the line that connects those points. I'm going to go y2 minus y1 over x2 minus x1, which is going to give me 32 over 2, which reduces to 16. The answer for problem 29, the average rate of change between 0 to 2 on this function is going to be 16, because 32 over 2 reduces to 16. Make sure that you actually were able to see what I wrote on the last problem, just in case the bottom of the screen was blipped out. Similarly, just in case you couldn't read the problem before that, just in case, because I blew up the screen and I'm not sure if there were times where I wrote stuff that you couldn't see. So I'm flipping back a few pages just in case you missed something. That's what I wrote for problem 26. You can pause the video and copy that down if you need. This is what I wrote for my answers to 27. That's what I wrote for the answer to 28. And there's what I wrote for the answer to 29. Next, you want me to graph piece functions, and there's no parabolas, they're only lines, so I'm going to make your life a little bit easier. 30, I want to graph f of x equals 3x plus 1, but only use values of x less than 2. And I want to graph f of x equal x minus 1, but only use values of x bigger than or equal to 2. For each one of these, I'm going to make a table of values. I usually do 3 points. For the first one, I have to use the boundary point, which is 2, and the numbers less than 2, which are 1 and 0, or others, but 1 and 0 are easy. For the second table, I have to use the boundary point, which is 2, and the numbers bigger than or equal to 2, which are 3 and 4. I'm going to create 2 graphs. I have to find y's. The first y I'm going to get, I'm going to plug 2 in for that x, and go 3 times 2 plus 1, which is 6 plus 1, which is 7. So on the top function, I'm going to plot the point 2, 7. Because the 2 doesn't have an or equal to, when I graph that, I'm going to do an open circle. Now I'm going to plug in 1 and go 3 times 1 plus 1. That's going to be 3 plus 1, which is 4. So I'm also going to plot the point 1, 4. Because it's not a boundary, it's going to get a closed circle. And then when I do 3 times 0 plus 1, I get 0 plus 1, which is 1. I'm going to plot the point 0, 1. So for the top graph, I'm going to plot the point 2, 2, 3, 4, 5, 6, 7. Open circle at 2, 7. And then closed circle at 1, 4. Closed circle at 0, 1. And this graph extends all the way to the left, but it doesn't go past the open circle. So that's the graph of the top function for x less than 2. Now I'll do the bottom one. I'm going to plug 2 in for x, and I'd get 2 minus 1, which is 1. I'm going to plot the point 2, 1. Because of the or equal to, I'm going to get a closed circle, or closed dot. When I plug in 3, I get 3 minus 1 is 2. I'm also going to plot the point 3, 2. When I plug in 4, I get 4 minus 1 is 3. I'm going to plot the point 4, 3. So for this one, I plot the point 2, 1, 3, 2, and 4, 3. And I only draw the part of the graph to the right of 2. So my graphs, I have 2 halves, a left half and a right half, essentially. And that's a reasonable picture. It's not on graph paper, so it's not probably stellar, but it's definitely good enough. 31, I have to graph a 3-piecewise function. Again, all lines just to make it easier. So the functions I have to graph are f of x equals x minus 5. The table I'm going to put are for numbers less than 5. I need to put the 5 in because it's a boundary, and the numbers less than 5 are 4 and 3. For the middle one, the f of x equals 2x minus 4, I need both boundaries, the 5 and the 7. And then I like 3 points, so I need a number between the 5 and the 7. I'll write a 6. For the last one, f of x equal to 2x. I need numbers bigger than 7. I need the boundary point, which is 7. And if I find each one of these y's, plot my points properly with open and closed circle, I'll make a decent graph. So for the top one, I'm going to go 5 minus 5 and get 0. This was going to give me the point 5, 0. This one has an or equal to, so it'll be a closed or a solid dot. And then when I plug in 4, I get 4 minus 5 is negative 1. I'm also going to plot the point 4, negative 1. And then when I do 3 minus 5, I get negative 2. I'm going to plot the point 3, negative 2. So I'm going to get that part of the graph done. I'm going to plot the point 5, 0. Those next points connect, but only go to the left of 5, 0. So for this graph, 1, 2, 3, 4, 5, 0, closed dot. And then 4, negative 1, closed dot. And then 3, negative 2, closed dot. And this graph goes on forever to the left because it's for less than or equal to 5, but it doesn't go past 5 to the right. For the next one, I'm going to go 2 times 7 minus 4, which is 14 minus 4, which is 10. I'm going to plot the point 7, 10, because the 7 has the or equal to here. I'm going to get a closed dot, or a solid dot. For 6, I'm going to go 2 times 6 minus 4, which is 12 minus 4, which is 8. The point 6, 8 will also get a closed dot. And the third one I'm doing 2 times 5 minus 4 is 10 minus 4, which is 6. For this middle one, 5 doesn't have an or equal to, so I get an open circle. So to do the middle graph, I'm plotting those 3 points, and the graph is just going to connect those, and that'll be it. So I need 5, 6, open dot, 6, 8, closed dot, and then 7, 10, closed dot. So this would be the middle portion, and I don't go beyond the 5, 6 or the 7, 10 because that's just for that confined portion of the graph. Last piece, I'm shoving 2 into the 2x function. So I'm going to go 7 into the, so I'm going to go unplug 7 into the 2x. I'm going to go 2 times 7 and get 14. I'm going to plot the point 7, 14. I get an open circle because the 7 doesn't have an or equal to. And then I go 2 times 8 and get 16. I'm going to plot the point 8, 16. And when I plug in 9, I get 2 times 9, which is 18. And I'll plot the point 9, 18. And this graph is going to go all the way to the right. So to finish up this, I plot the point 7, 14, open circle. And then the point 8, 16, just fudging on these because I don't have graph paper. I don't need to be that accurate. And then 9, 18. And that portion of the graph doesn't go past the 7, but it goes on forever to the right. So this would be a very reasonable picture of this piecewise defined function. So I divided each of the pieces. I made sure to get the right open and closed circle on the 5. The top graph got the closed, the middle graph got the open. On the 7, the top graph got the open, the middle graph got the closed. And that would be a reasonable picture. Okay. Next bunch of problems are a bunch of non-algebra problems. They're all from section 3.5, and that didn't have a lot of algebra. I just need to describe how the graphs get moved based on what's in the parentheses, where the negatives are, and so forth. So problem 31, this graph is going to have the same shape. It's going to be a parabola because of the square, as f of x equal to x squared. We'll just say it's the same shape as x squared. The plus inside the parentheses is going to move it to the left 2 units, and the minus 4 after the square is going to move it down. So if you just said down 4, left 2, I would be content with that. We can get much wordier than that, but there isn't any need to get wordier. For 32, the graph is going to have the same shape as the square root of x, which is a half a parabola on its side. The minus here is going to reflect it because it's in front of the square root over the x-axis. If you just said it flips it over, I'm content with that. The minus 3 under the square root is going to move it to the right 3, and that minus 5 is going to move it down 5. So if that's all I saw on your test, that's completely fine, just so you understand how each minus or plus sign impacts the graph, and you just use some words that tell me that. You don't need to get that wordy. 33, this negative moves the graph to the right 3, and that plus moves the graph up 4. So if you just said up 4 and right 3, I'd be content. 34, a negative inside the graph with attached to the x is going to reflect it or flip it over the y-axis. So a negative in front of an x, or a negative x, reflects it over the y-axis. This plus 2 moves it up 2. And I didn't say it has the same shape as the square, but I could have. For 33, I could say it has the same shape as the absolute value of x, which makes it a v. For 34, I can say it has the same, but we don't have, just the key moves is all I'm really looking for. You don't have to do the same shape part. For 35, the negative in front of the parentheses reflects it over or flips it over. It's going to reflect over the x-axis, and the minus 3 inside the parentheses moves it right 3. And that's all I need for those problems. I don't need long explanations, just so you understand each minus or each plus in the problem is going to impact the graph, and you have to understand how each minus and each plus impacts the graph. 36, I need to write equations. I give you a base function and tell you what needs to be done. Oh, I did leave myself room for 37, but that's okay. So, and again, I'm going to be lazy here. Either I can write a new named function, or I could do something more elegant with the name. So I'm going to use g of x for 37, 36, and 38 for the name of my new function that I create. There's no algebra to do. For 36, I need a function that has the same shape as x squared, so I know I need an x squared. To shift it to the left 3 units, left is inside the parentheses, plus makes it go left, so this x plus 3 inside of parentheses will move a graph left, and then the down 2 is a minus 2 after the parentheses. So up and down are after the square, left and right are inside the parentheses. 37, I want the same shape as the square root of x, so I know I need a square root of x, a square root in the problem, but reflected over the y-axis. To reflect over the y-axis, you change an x to a negative x. And that's the only thing that needed to be done, so that's the entire answer. 38, I'm going to get a square again because it wants the same shape as x squared. Reflected over the x-axis, you get a negative in front of the parentheses. To the left 4 units, I get an x plus 4 inside the parentheses with the square, and for the up 2, I get a plus 2. Hopefully, you did so many of those when we did section 3.5 that these went really quickly. These are the kind of problems where I can't give you a lot of partial credit. They're either right or they're wrong, so you just have to nail them. All right, I think that's the end of section 3.5, and now we're into the word problem section. And I put 2 word problems. There's only 2 word problems on the review, so there can't be more than 2 word problems on the test. And I'm trying to hold your hand through these a lot. Again, these problems without the hand holding are problems from the brief calculus book, so you could very likely see those again at some point. So 39, I just took the problem that was in the homework and I changed one number on it, and the rest of the instructions are the same. In the homework that we did for 3-6, that 2000 was a different number. So this is completely just, in some sense, review. Hopefully, because it's a review section. So I want to construct a fence, and it says one of the regions borders a river, so I really only need to construct 3 sides of the fence. I'm going to call this the length, give it an L. I'm going to call these the width, give them W's. Although it really doesn't matter, you can interchange your W's and your L's and still get the right answer. So I have 2,000 meters of fencing. So the perimeter, the amount of fencing I have, the perimeter of this has to equal 2,000. So the amount of fence I have has to be the 2,000. The amount of fence I use is the amount that I use for the length, plus the amount that I use for the widths, because there's 2 widths, there's 2 W's. I'm going to solve this for L. I get L as 2,000 minus 2W. That's the expression for the length of the field. The length of this field is going to be L equals to 2,000 minus 2W. So I drew a picture. I labeled my lengths and my widths. Usually you make the length run parallel to the river, but it wouldn't be wrong if you didn't. Your algebra would look different. You'd get the same numbers for an answer. Ultimately, your lengths and your widths would be backwards from mine, but they'd be the same numbers. The area of this region, area is just length times width of a rectangle, even if one of the sides is bounded by a river. In this area equation, if I change the L to 2,000 minus 2W, I get 2,000 minus 2W times W equals the area. That's the area equation that we wanted. I took the generic area formula for a rectangle, length times width, and plugged what I got in part A in. So the area formula for this is going to be 2,000 minus 2W times W. Now I'm going to graph this on my calculator. I'm going to give you a window on the test to use, because if I don't, it makes it hard to figure out what you need to figure out. So I'm going to graph y equals, I'm going to go parentheses 2,000 minus, I'm going to go 2x because I can't use w, times x. Now I'm going to hit my window. I'm going to make my x's go from 0 to 1,000 because that's half the amount of fence that I have. And then for the y's, I know my area is at least going to be 0. I'm not sure how big it's going to get, but I'm going to put 5,000 for a guess. I'm going to hit graph. If I can see the vertex of the parabola, I'm good. If I can't see the vertex of the parabola, then I'm not good. And I'm not so good here, really. Window, second table. Oh, my y's are very big. When I look at this, my y's go up way, way high. So I'm going to make my y's get way higher. I'm going to make my y go to 100,000. And again, I'll do this work for you so you don't have to play on the test. Once we get to a calculus class, you won't have to rely on your calculator. It's even higher than that. Let me make it to go to 500,000. And again, you won't have to do this playing on a test. Oh, that's barely high enough. So that was a reasonable picture. Now I'm going to find the vertex. The x-coordinate of the vertex is the optimal width. The y-coordinate of the vertex is the area at that width. So let me find the vertex by going second, calc, going to the maximum feature, trace to the left of the vertex, hit enter, trace to the right of the vertex, hit enter, and then get as close as I can to the vertex, hit enter. I'll probably have to round the x-coordinate, but I didn't. So here, the value of the w that leads to the maximum area is 500. So I can answer part C, a width of 500 feet gives me the maximum area. And I could actually do part E. The maximum area is 500,000 square feet. So for this particular function, the vertex gives me the optimal width and the maximum area that you can enclose. It doesn't give me the length, so I'll do some algebra to get the length. To get the length, I'm going to use this formula, L equals 2,000 minus 2W. So I'm going to go solve for L. L equals 2,000 minus 2W, but the optimal length is 1,000 feet, so I get 2,000 minus, the optimal length is 500 feet, so I get 2,000 minus 2 times 500, which is 2,000 minus 1,000, which is 1,000. So the optimal length for this is 1,000 feet. So ultimately, it's just part A and part B that you have to be careful about, because C, D, and E are all just going to be calculator exercises for us. So I came up with an expression for the length of the field by creating a perimeter equation and solving it for L. Came up with an area equation, replaced the L with 2,000 minus 2W, graphed it. The X and the Y coordinates gave me the answers for C and E. I needed to do a bit of algebra for D. And I'll give you the viewing window on the test so you'll have to play with that. Okay, one last problem. It's a little bit harder. It's the cost word problem, but it's not hopefully horribly hard. It'll be harder for me to get the window appropriate. So first thing, I have 1,000 square meters of fencing. I'm building a 3-sided fence, and it says, again, I'm going to call these sides width, so I'm building only 3 sides. Now the sides have costs. It says, so this is the existing fence. Just like the river, I kind of put it in the same position. It says that material for the fence costs $10 per meter for the 2 ends and $6 per meter. So the length is going to cost me $6 per meter. The widths are going to cost me $10 per meter. Now I need to come up with equations. I don't have the perimeter like I did in the last problem. In the last problem, the first thing I did is come up with a perimeter equation, because the amount of fence I had was the perimeter and not the area. So when I go to do my work for this particular problem, that 1,000 is the area of this region. So that 1,000 is going to equal the length times the width of this region. And I'm going to solve that equation for L by dividing both sides by 1,000. So because the 1,000 was a area as opposed to a perimeter, my beginning, I set the number equal to the area as opposed to the perimeter. So when I do this, I'm going to get L equal to 1,000 over W, and that's solving the equation for, that's the equation for the length of the field. Now I need to come up with a cost equation. The cost, which I'll write as C, is going to be the cost of this side plus the cost of this side plus the cost of this side. The cost of this side is 10W. The cost of that side is 10W. The cost of that side is 6L. So the cost is going to be 20W plus 6L, and I'm going to change the L to 1,000 over W, so I'm going to get cost equals 20W plus 6, and then times 1,000 over W, which is 6,000 over W. So my equation for the cost of the field, my cost is going to be 20W plus, and then I'm going to write 6,000 over W. Once you get that, you're done. Everything else is just going to be jamming this on my calculator, getting a reasonable window, which is going to be some work for me to do right now, so I might have to fudge. Again, on the test, I'll give you the viewing window that will work just fine. So now I'm going to graph this function. The x-coordinate of the vertex is going to be the width that gives the minimum cost. The y-coordinate of the vertex is going to be the minimum cost. I have to do algebra to find the L, but it's minimal algebra. So now I hit my calculator, y equals clear 20x plus 6,000 over x. What happens if I just say graph? Probably horrible things happen because my cost won't be that much. Let me tweak the window quite a bit. Let me tweak the y max down to, so I'm building a fence that's 1,000 square meters. Let's say the fence is going to cost $5,000. And it's can't be that big. Let me make this 100. And again, I'll do that playing for you, so you won't have to worry about that. But that's probably actually a nice window. Little Nike swoosh graph. So this window, 0 to 100 on the x's, 0 to 5,000 on the y's, is suitable because I can see the minimum, and that's what I'm looking for, the minimum cost. So now I go second, calc, go down to the minimum feature, trace to the left of the bottom, which takes a long time. Then trace to the right of the bottom, and then get as close as I can to the bottom. And, oh, really? Well, that's something I'm not going to round much better. So when I made this problem up, I thought I would have nicer answers, but it's okay that it doesn't have such nice answers. I'm going to take this and say the optimal width is 17.32 meters. The cost is going to be $692.82. Fortunately, this isn't a calculus problem that we're doing algebra because it would be very messy. Let me redo this again to make sure I get that 1732 and I didn't make a computation error here on my calculator. So left bound, right bound, and guess. Yeah, that just isn't something I can round any better. So I'm going to say the optimal width is 17.32 meters. The cost is going to be $692.82. So let me put those in here. So the value of the width that leads to the minimum cost, the width is going to be stole from my calculator. I don't want to carry more than 2 decimals. And I'll make it so the test doesn't come out to be a decimal. The cost is going to be, again for that, I'm not going to round past 2 decimals because money makes sense only as 2 decimals. So I've got the vertex of the calculator gives me the optimal width. It gives me the minimum cost. I need to find the L. I find the L by plugging in my width of 17.32 into that equation, and again I'm going to round that again to 2 decimal places. So I'm going to go 1,000 divided by 17.32, plugging the W into the length equation, and I get 57. I'm going to round that to 0.74. So the optimal length is 57.74, and then because this is in meters, I'm going to call this in meters. And that's everything there is to do for this problem. So the big bit of these word problems is coming up with the initial equation, the equation that needs to be maximized or minimized, and then being able to get the components of the answer from your calculator, which is parts C and E of all my questions, and then doing the little bit of work to find part D. So that's the entire review. It's a rather long review. But it's a good chapter because so much of this chapter comes up again in calculus. So this, when you go to do your calculus class, this little step-by-step help that I have here, you might want to dig that back out because in a calculus class, you're going to get that without the little holding your hand steps. But these are the steps that you'll have to use. All right, so come visit me if you're feeling a bit overwhelmed so that this test is a good experience.